All right, welcome back, everyone. So here we're going to take a look at the two long questions for the AP Physics 1 exam 2023 FRQs that were publicly released. So what we have here is our experimental design question. It's a little bit kind of weird in the sense that you're actually not even asked to design an experiment in this one. It's actually all just data analysis, which actually surprised me a lot. I was not expecting that. But let's go ahead and take a look at it anyway. So we're trying to determine the acceleration of a cart that was dropped from rest at the top of a ramp. Indicate which quantities could be used to graph a straight line so that you can get the acceleration. You may use any remaining columns as needed to record any quantities that are not already in the table. So what we actually have here is position and time. And the thing that we already know about a car moving down a ramp is that it should have a constant acceleration if we do neglect air resistance, which of course we are because this is AP Physics 1 and the question doesn't ask us for air resistance. So what I would say is on the vertical axis, let's go ahead and plot X. And then on the horizontal axis, let's go ahead and plot time squared, position squared. Now, because I'm currently exporting my video for the short answer questions, I'm going to try to avoid using my pen as much as possible for right now. But I'll go ahead and try to ensure that everything is clear for you. So what we do have to do, right, because we're not plotting position versus time, but instead position versus time squared, according to the kinematics equation that is missing final velocity in there, right? We can say initial velocity is 0. We know that. We know we have a constant acceleration, but we don't know what the final velocity of the car should be. So if we say that we can use the kinematics equation missing final velocity, we can get that x should be proportional to time squared. So I do have to plot time squared, t squared, and the units, of course, should be seconds squared then. So in terms of that, all I actually have to do to get those values is just take the square of everything that is provided to me. So if I go ahead and do that, 0.39 squared is going to give me 0.1521. You do actually have to fill out all of these data points. I know that it's a little bit tedious, but the question does say that we have to, so, we kind of have to. 0.3481 for the next one. If you didn't fill out this table with your new data points, you would probably get a point off, I would say. Actually, you would definitely get at least something off. I think that the amount that you would get would be 1 point. I don't think you would get any more than that, which is good. But we have two more numbers. 0.96 squared is 0.9216. And then 1.2 squared, we're almost there, 1.44. Good. So those are the numbers for time squared that we have, and now we can plot position versus time squared. Now, here's where things get to be a little bit tricky. I am actually going to have to use my tablet, so I'm just going to keep my fingers crossed it's actually not going to lag too much. All right, clearly scale and label all axes, including units. Yeah, and draw a straight line that best represents the data. All right, let me go ahead and try to do that as best as I can. So we got time squared. Oh, wow, it's actually not lagging too much. All right, time squared, t squared, which is in units of seconds squared. And then on the vertical, we've got position, which is x in units of meters. Now, you might see that I haven't actually cleared the time squared values, and that's actually because I'm going to need them as I'm plotting. So let's start at 0, 0. Right, how many big lines do we have on the horizontal axis? 1, 2, 3, 4, 5, 6, 7, 8. So I think that a good scale to use would be 0.2 seconds squared. So we get 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, and then 1.6. I know that leaves a little bit extra room on the right side, but better to have extra room than running out. Now, if we do go back to the previous page, we go all the way up to 0.55 meters. So 1, 2, 3, 4, 5, 6 lines along the vertical axis. Let's just do that in 0.1 meters. That way we have a little bit extra room at the top as well to help us with our best fit line. Good. And now we have to go ahead and get plotting. So what I'm actually going to do is I'm just going to go ahead and trace over all of these position values, or actually I'm just going to write them in this extra column here. Again, you wouldn't actually fill out this column with all of the position values again, because you're not doing anything to them. You're already given the position values. The only reason I'm doing it right now is actually so that if I just go ahead and I go back to the graph, I can actually see both the X and the Y coordinates without continuously switching. So we get about 0.15, 0.006. Our first data point would be right there. 0.34 is going to be pretty close to the 0.35 mark. And then we go up to 0.14 right there. 0.6-ish. 0.24, I think right there. 0.92, that's halfway between 0.9, 0.95-ish. And you go up to 0.37. All right, we're starting to get into some bad data points here. And then 1.44 is close to 1.45, and we would go all the way up to 0.55. So about right there. All right. And now we have to go ahead and draw a straight line. I'm on the computer, so I'm going to make this a little bit easier for myself and just use a perfectly straight line. And that looks decent, actually. Yeah, perfect. All right, using the line, calculate an experimental value. Well, let's use that equation that I mentioned earlier. The kinematics equation missing time says that delta x, which would actually be x, I guess, right, in this case, because we would start at x is equal to 0, that should actually just equal 1/2 acceleration times time squared. Therefore, the slope should actually equal 1/2 acceleration, because if I take x over t squared, that's like rise over run, and all that's left is 1/2 acceleration. Therefore, acceleration should be 2 times the slope. Now, we do actually have to calculate the slope. Let me go ahead and choose 2 data points on my line, and we can use those to calculate the slope. Right there looks good in red, and then the second one could be right here. So what those 2 data points are going to be, my slope is going to be computed using them, right? Rise over run. The first rise is 0.54. The first y value, the second y value, and the first one is 0.8-ish, 0.08. X value, 1.4 minus 0.2. And if I go ahead and actually compute that slope, let's go ahead and pull out my calculator. 0.34 minus 0.08, so 0.26 on the top and 1.2 on the bottom. So the slope is going to actually be 0.217. So therefore, if I multiply that by 2, I do actually get that the acceleration is going to equal 0.43 meters per second squared. As soon as asked to determine an experimental value for the acceleration due to gravity, well, we know that without friction, the acceleration down a ramp should be g sine theta. So the other additional quantity that we need is the angle of elevation for the ramp, theta for the ramp. That's actually all we need. Once we have that, we could say A, 0.43 is equal to g sine theta, and then we could calculate g. All right. What is a physical reason that could lead to a significant difference, a significantly lower experimental value of g in this case? Well, what I could say, right, we can't actually use friction or air resistance, which are the obvious choices. But the thing that we do know is that if you were to maybe start by, let's say that you were to start by giving the car a little push up the ramp, right? So if I go back to the previous diagram, you can see that the cart was released from rest. And we're trying to actually come up with a physical reason, not a human reason, I guess. So I guess what I would maybe say is that the cart's initial velocity was up the ramp at time t is equal to 0. The reason why that would lead to a lower acceleration is because we know that acceleration should be proportional to the slope, right? So g should be the experimental value of g should be proportional to the acceleration, which should be proportional to the slope, which is proportional to position over time squared, right? If the cart had an initial velocity up the ramp, what that would actually do is that would make the cart's recorded position would be lower than it should have been at, and I'm just going to go ahead and erase all of these numbers now. We don't need them for the rest of the problem, it looks like. So this would actually cause the car's position to be lower than it should have been at any given point in time. Decreasing the slope of the graph, and therefore acceleration in g. Good. I think that would be pretty sufficient. All right. Student wants to confirm that the acceleration is the same going up and down the ramp. Student gives the car a quick push and then it comes to rest. Positive x is up the ramp with the origin at the top. All right, that's important. So what this actually means, right, is that if positive x is down the ramp, right, and the origin is at the top, we would start with an initial position, and we should expect this to be a quadratic function, right, something along the lines of that. And the reason why is because, again, it should follow a kinematics equation. In addition to that, we would expect the velocity to actually be positive at the second half when the car is going down. And because we would expect very constant acceleration, therefore what we should get is we should get a graph that is represented by a straight line because the slope of velocity time is acceleration. Good. All right, that's it for the experimental design question. Let's go ahead and take a look at the qualitative quantitative question then real quick. This one looks fun. A small block is attached with a spring constant and the rod is attached to a motor. When the rod is not rotating, you have an unstretched length. Good. Okay. This is a circular motion and oscillations question. The two units that I'm not like terrible at them, but they're ones I'm definitely a little bit less comfortable with. I guess let's just take a look at it. At time t is equal to 1, rod is spinning, circular path, constant velocity, and a stretch distance d1. Time 2, different velocity, um, different distance stretched. Okay, greater distance stretched, in fact. All right, so that would have to mean that you have a greater radius. Which I presume is going to be important. All right, so on the following dots, draw the forces exerting on the block by the spring, just by the spring, so you don't actually need gravity and normal force, which is good, and they must, the relative lengths must represent the relative magnitudes of force. All right, so we should have FS1, right? Does it actually say to label? No, we don't have to label, which makes sense because it's just one force that they're asking us to draw. All right, so I would expect for T1, the spring force should be pointed to the right towards the center. It should have some magnitude. Now, we don't actually know how much bigger D2 is compared to D1. So all we would actually have to do is have a longer spring force in the second drawing pointed to the right. All right, referencing D1 and D2, describe your reasoning for drawing the arrows the length that you did. Simple. Hooke's law, right, states that the spring force, right, is equal in magnitude to just k times displacement from equilibrium, right? For T1, delta x is equal to D1, and for T2, delta x is equal to d2. Therefore, the spring force should be stronger at time 2, at t2, since d2 greater than d1. All right, here we go. This is actually what I was kind of expecting them to get at. Is the tangential velocity greater than, less than, or equal for t1 compared to t2? Where is it going to be greater, less than, or equal to? All right, well, what I would say, justify your answer without using equations is I'm going to go ahead and do the justification first, and then I'll actually use that for my reasoning, right? At time t2, the block experiences a greater spring force, as we mentioned above. So the acceleration of the block required to keep the block in its circle is higher. What that would mean is that, let's see, if d2 is greater than d1, and I'm just kind of thinking aloud right now before I continue with my justification, right? If d2 is greater than d1, that should have lowered the acceleration required to keep the block in the circle, right? So therefore, this would imply that the speed has to be higher. Since d2 greater than d1, it follows that this higher required acceleration comes from the fact that the block has a higher speed at time t2. All right, so I'm not actually referring to equations or really even using them, but what the heck just happened there? But I am kind of drawing on how to relate all of that stuff in order to say that V1 is less than V2. I apologize. For some reason, it's not actually letting me. Is it going to let me? No, it's not going to. Okay. That's nice. It's not going to let me redo that text. So I guess I apologize about that. Please go ahead and yeah, I guess what you're going to have to do is you're going to have to go ahead and rewind the video if you didn't catch all of my justification. But let me state it in words. Right, again, higher net force at time t2, higher acceleration required to keep the object in circular motion. Since the circle is larger, you would expect that higher required acceleration to come from the fact that the block is moving faster. All right, there you go. All right, we're almost done though. Just three more parts left. Consider the scenario where you travel a circular path, derive an expression for the net force exerted on the block. All right, that's not too bad. We kind of already did that. We said that the net force should be the spring force, right, which is just going to be equal to K0, and that's just going to be actually K0D, right, because it's just going to be the displacement from equilibrium, right? The unstretched length is L, so therefore the stretched displacement from equilibrium is just D. So it's just going to be K0D. Derive an expression for the tangential speed. Well, what we do know is that we do know that AC is equal to V squared over R. That's on our equation sheet, right? And that also has to be equal to net force over the mass m0, right? So what that's going to tell us is that's going to tell us that V squared over R, right, which is going to be equal to V squared over L plus D, because that's how far we are from the center of the circle, is going to equal K naught D over M0. Therefore, right, V is going to equal the square root of K0D L plus D over M0, right? And clearly with that expression, right, that does agree with our reasoning, right? Because, and I'm going to go ahead and type this one again, right? Because what our equation says is that since D equals D2 is greater than D is equal to D1, right? My equation states that the speed should be higher, given that L, K0, and M0 are all constant. All right, and that's it. That's just stating why our equation does justify that we should have a higher tangential speed in time t2. All right, that's it for the long FRQs for this 2023 AP Physics 1 exam. I might do some actual like content videos next. I don't know. I don't really like waiting a year to record in between videos and only doing FRQ solutions. If you guys would like for AP Physics 1 or AP Physics C content, let me know in the comments which topics you would maybe prefer me to cover, and I can maybe go ahead and take a look at some of those too. Yeah, but otherwise, thank you for watching, guys. As usual, if you have any questions, comments about my videos, make sure to leave a comment down below as well too. And have a great day, everyone. Thanks again for tuning in. Take care.